Hi, this is Dr. Pello, and this is video 5 of how to take correlations and build latent variable models. And today we're going to reach a point where we build a full model that actually has a relationship between two latent variables to make the case or the point as to why it's important to do this and what it accomplishes for us. So first I need to pull up a data set. I am in Amos. I'm going over here to this little box that looks like a bunch of data files and select data, file name, and go over here to documents that have been downloaded. And pick up this example, hit OK. And I'm going to go ahead and build a couple of latent variables. 1, 2, 3, and we keep them kind of simple. And another one. 1, 2, 3. Rotate button, hit rotate. And I'm going to try and line this up using the little truck to move that variable kind of straight underneath. Arrow down. So here I have two latent variables, and now I've specified that this one is going to predict this one. This top one's going to predict the one on the bottom. If I'm predicting something, I have to allow for there to be error. So I have to allow for the possibility that there's not perfect prediction. There's another button over here that says add a unique variable to an existing variable. You can click on there, click it again, a couple of times, spin it around to where it's on the opposite side. That's going to be my error term. So just like if you're saying y, an outcome variable is equal to x, we say x plus, there's some amount of error, and this is my some amount of error that's being added to that. Okay, so the variables that I'm going to do here, let's go ahead and do a pointer. I'm going to make this what's called external influences. And this one is authentic living. Now, there isn't a real good reason to expect that there's a causal relationship from this theoretically. I'm just using the data set because it's handy to draw out examples. But external living is the notion, sorry, rejecting external influences. Let me put that in there. Rejecting external influences is the idea that if someone is pressuring me to do something that I don't want to do, that I basically feel free to go ahead and say, no, that's not me, that's not what I want to do. I'm not going to pay attention to those outside influences. I'm going to let my own moral compass be my guide, and hence that should result in more authentic living. So the two are thought to be connected. I think they're going to be less connected than what I would have thought theoretically in this model, but it's another story. Let's just see how the math works out. So I go over here to this box, and it is the list of my variables, and I'm going to choose 3 variables that assess authentic living. Items 1, 8, and 9. And 3 that assess rejecting external influences, 3, 4, and 5. And there we go. And now I'm going to go to my plugins. I'm going to name the unobserved variables, and it basically names all of my error terms. These are two different types of error terms. This error 7 is for like what were the error term in regression, and these error terms are the separation of error from common variance that occurs from a measurement perspective. So you got kind of measurement error terms and a structural error term. And so we have our model set up. Two latent variables. We're estimating the relationship between those two latent variables. And so I'm going to go over here. I'm going to go ahead and do this as unweighted least squares. My output, I'm going to ask what are my standardized estimates, sample moments, implied moments, residual moments. And it's going to be good enough. And I need to save this for it to run. So sample structural model. Let's go ahead and stick it in with documents. And it ran. And these are the unstandardized estimates, and here's the standardized estimates. Unstandardized, standardized. Notice that the unstandardized basically puts more information in there about your errors and so forth, but let's go with standardized so we can focus on the correlational tracing rules. There's a result. We have a correlation of 0.14, and I'm going to take this and copy it and paste it over into an Excel spreadsheet and meet you over there to talk about these results in Excel in just a moment. Let's do one thing before we look at that. Here's our output. We had 8 degrees of freedom. Here's our sample moments. Here's the original correlation matrix that we're working from. Here's our estimates, and here's the standardized regression weights. Here's that 0.138, which is the 0.14, and the rest of these are factor loadings. Okay, here is my model in Excel. And what I've done is I've taken some pictures of things that I've already run. Let's start with the correlation matrix. That is the data that we're working from and what we're trying to reproduce. So we have 3 measures of rejecting external influences. We have 3 measures of authentic living, and we expect these correlations to be, since they're measuring the same construct, to be high, and they're reasonably high. So we have a 0.478, a 0.531, a 0.639. These are the correlations between the assessments, the 3 items that measure rejecting external influences. And then for authentic living, this is what we've done in the first few videos. We have the 0.624, the 0.639, and the 0.708. Hopefully those ring a bell from the previous videos. And they give us our authentic living construct. And so what we've been working for here is to come up with our authentic living construct. And now we've added on to that a rejecting external influences latent variable or construct. But we are also looking at the relationship between these two. and that's going to change those estimates slightly, so they're not exactly the same as what they were before. So we also have in this correlation matrix over here the relationships between our measures of rejecting external influences and those assessing authentic living. And with 3 measures on one side and 3 measures on the other side, we end up with a total of 9 correlations going between these, right? So variable 1 from rejecting external influences has 3 correlations with 3 measures of authentic living of 0.142, 0.065, 0.127. X2, here's the 3 correlations. X3, here's the 3 correlations. So these are between the constructs. Within the constructs, in the upper diagonal, the lower diagonal, we have 3 variables assessing in a triangle within a construct, and then in a square between the constructs, we have the correlations between those. And the average correlation, if you take all of these and average them, and I did that over here, that average is 0.08733. That's the average of those correlations. Now, what would researchers typically do if they're not doing latent variable modeling? They would typically take the average of the rejecting external influences, equally weighting each one of those, so they all have the same weight. And then they would do the same thing for authentic living. Items 4, 5, and 6, just average those together and create a variable. And I did that in SPSS. And then I correlated those 2 variables with 3 items on each of them, equally weighted, and the correlation was 0.118. Now, it makes sense that the correlation between the averages of the items on a scale is slightly larger than the average of all of the individual correlations. And it's because averages should catch common variance, thereby reducing the impact of measurement error. And so in that way, it's doing a little bit of the job that we expect a latent variable to do, but it doesn't quite go all the way. And you'll notice that we started off with the 0.087. Here with the averages, it's gone up. The correlation between the constructs of rejecting external influences and authentic living, has gone up slightly, but it hasn't gone up quite to our estimate based upon the correlation between the true latent variables, where the correlation's now gone up to 0.142. How do we explain this? Well, part of it is that we are getting not just the items averaged together, but we're getting weightings for those items. And the weightings are strategic, designed to capture the common variance by weighting the items that seem to best represent the common variance by correlating most highly with the other variables, and thereby leaving error variance more to the side for those items that are less diagnostic. It's not the only thing that's going on, though, and we see that through the tracing rules. So let's talk about and get to the end point here. How are we going to set up a latent variable model using Excel? Okay, let's start with the actual correlations that we're using as input. Notice that from over here, I've taken the 0.478, the 0.531, the 0.639, and I've plugged those in as my actual correlations representing the first three variables. Going down over here, we have the 0.624, 0.639, and 0.708. And then the correlations in the box part of the matrix, representing the relationships between all the items assessing the constructs. I have listed 0.142, 0.065, and so on, all the way down to 0.083. And then if you check out the code here, I am capturing, I'll just rewrite it, the average of all of these correlations, right? Over here, I've designated what's going on. I have the correlation between variables 1 and 2, 1 and 3, 2 and 3, between 4 and 5, 4 and 6, 5 and 6, and then 1 and 4, 1 and 5, all the way down to 3 and 6. Now, over here, on this side, we have our model specifications. What are we trying to solve for? We're trying to solve for paths A, B, C, M, N, O. Those are all loadings on the two constructs respectively. And then G, the path between the constructs. So we've already done the equivalent of these latents before. Let's go ahead and start over by making our factor loadings with start values of 0.5, the path between the constructs 0.5, and these are blank spots. Remember, we have our implied correlations are based upon the tracings. And so we've done this before. So equal path A times B. A times B gives me the tracing for the relationship between R1 and 2. Should reproduce that 0.478 correlation once I have satisfactory loadings for A and B. Go down over here, we'll do one for, say, M and O. That's the correlation between variables 4 and 6 on the second construct. So that is path M times path O, right? So here is X4, here is X6. That correlation is reproduced by going down path M, changing directions, and going up path O, and the coefficients in the model get multiplied together to reproduce the correlation. Now, where things really get interesting is reproducing the correlations between the latent constructs. And here we have, let's say if we're looking for the correlation between X1 and X4, X1 is a rejecting external influences measure, X4 is an authentic living measure. I start by going backwards down the arrow, that's path A, switch directions once. I go path G, and then path M, same direction. I'm not changing directions twice, that's important. And so there I end. Three paths are multiplied together. A times G times M is designed to reproduce the correlation here of 1.42. It equals to A times G times M. And what I've done is I've already done this. If you look at the codes up over here, here's the second one, A times G times N. Here's another one, A times G times O. Skip on down over here, B times G times O. Skip on down over to here, C times G times N. So all the possible pairings, tracings that give us the relationships between this set of variables, x1, x2, and 3, and this set of variables, x4, x5, and x6, have been done. You remember that over here, we've specified error. And the way that we write error, using for the least square criterion, is we take the actual correlation minus the implied correlation based upon the model tracing. Square it, error squared, that's how far we are off, and that's our error. And basically that formula just gets copied all the way down. We're not doing anything with respect to this average. It's just there as a reference. It does not enter in as an error. Our errors are based upon actual correlations, and this is not an actual correlation from our data analysis. It is the average of all of these correlations between the constructs. And again, is this there for the comparison? This should represent our new average, but based upon the weightings of the factor loadings. Okay, last but not least, here at the bottom here, I've written this as the sum of all of these errors. I'll reproduce that again. The sum of all of these errors squared. Okay. And now we're going to go to our solver. If you haven't watched the previous videos that I've done on Excel, both of those show how to get the solver. Go over to your solver. You basically say, what I want to do is minimize the sum of the error squares. The sum of the error squares is just the cell here. So capture that cell. And then say, I'm going to change these model specifications to reduce that error down to a minimum. Solve, hit OK, and there's my model solution. And this model solution gives me loadings and the relationship between the constructs that are exactly equal over here, 0.65, 0.78, 0.65, 0.78, 0.80. Once you round it, 0.14. Right here I have a 0.14 for my G. So it is matching. And you'll notice that this pathway is higher, not only higher than the average of the correlations, but higher slightly than the correlation of the averages of the items. Again, that's because these loadings here are differentially selecting to weight the items that are most diagnostic of true variance in the construct, reducing the weighting for those that have more error. But not only that, the act of actually doing the model with this estimation strategy that is working via the tracings tends to pump up this correlation, because I'm not just, in order for me to get from x1 to x4, I'm not just going through G. I'm also going through A and M which are now values less than 1 in standardized form. That means in order to reproduce the correlation, this path has to compensate for the loadings being less than 1. And so they get pumped up higher in order to try to reproduce the average correlation of 0.087. If we actually look at the average of the correlations as reproduced, let's see what we get. It's really close to 0.087. It's 0.0857 is the average of the reproduced correlations. This is the true average. This is the reproduced average. But this 0.142 is the relationship from a latent variable model. It's the relationship basically reducing error, or we could say that it is the proper way to get the true, to estimate the true relationship between these variables by disattenuating the correlations as a function of measurement. But instead of it being a direct disattenuation, it instead is indirect as a function of forming latent constructs that systematically try to capture true variance. Okay, that's it for video number 5. I hope you've enjoyed learning and seeing how this is done in Excel. Hope to do more videos. I'll talk to you later.